So I will let you know.
How do I? So do you mind if I just move this out of the way? Could we just maybe move it out of the way? Because I like to pace up and down a bit. So
It's just a little bit tricky because here's the pointer. It's actually remote control for the mouse there. And the middle one actually goes forward and the lower one goes backwards.
forward.
Should be. The mouse is working, right? The pointer
The mouse pointer is working.
but the forward button
Okay, it's not a laser
No,
pointer.
it's not. It's not. It's a remote
Okay,
control
right,
for the
okay, fine.
pointer.
That's okay.
But the
So
forward,
is this a touch screen?
no.
No.
Try again. Now it's working.
Okay. Okay, very good. All right, I think we're here.
So just introduce you. You know when you're about
So-
10 minutes before the end.
Hang on a second. I need a. Sorry, is there a clock? There's no clock. Hang on. Let me just get my phone. No, I'll get my. I need to keep an eye on the clock. Okay. So, hang on. I've got a. Whoops. Shit. Hang on. How is that I want? Okay. Sorry, what is the time? Is it 10 past 9?
We end at 10. It's 10 past 9. Yes.
Ah, Jesus. Okay. All right. Okay. So,
Okay, so good morning, everyone. So please let me just kindly ask you to turn off your cell phones or put it in silent mode. And now we're going to have the first lecture of the day by Professor Valentini. He's going to talk about Beyond the Born rule in quantum gravity. Thank you very much.
thank you very much. Apologies for being late. Blame Nelson. Where's Nelson? There we go. There we go. He picked me up and he was late. Anyway, so my subject is beyond. Sorry, I like to have space here. Okay, beyond the Born rule in quantum gravity. These ideas this talk is based on these two papers, which came out in 21 and 2023. I can't really see. Let me stand here. Okay, 3 main points I'd like you to remember from this talk, apart from the fact that I started late and it was Nelson's fault. That's the most important point. But there are the actual substance of the talk. There are 3 main points that I'd like you to remember. 1 or 3 claims, if you like, that there is no such thing as the Born rule in quantum gravity. Second point is that the Born rule emerges only in a semi-classical regime, where you have, say, a quantum field on an approximately classical background spacetime. It's only in such a regime that you can have the Born rule, which emerges by a dynamical process of relaxation. Thirdly, there is a little bit more speculative in the sense that I'll explain, is that quantum gravity corrections to the semi-classical regime can make the Born rule unstable. So can everyone hear me, by the way? Okay. Okay, so the main point. So let's flesh out the main point a little bit. So when I say no such thing as the Born rule in quantum gravity, I'm talking about the Wheeler-DeWitt equation, and I'm making the point that the modulus of psi squared, the usual Born rule density that one might naively write down, is not a probability for reasons I'll explain. When I say the Born rule emerges only in the semi-classical regime, what I mean is some approximate situation where I have an approximately classical background space-time with some quantum fields or systems propagating on it, and you have an effective time-dependent Schrödinger equation. In that situation, the Born rule can emerge by a dynamical process of relaxation. When I say quantum gravity corrections to the semi-classical regime can make the Born rule unstable, what I mean is that an initial distribution, an initial probability, now the mouse is not working. And what did I do? The top one, the mouse is not, no, it's gone. It's gone. Okay, the mouse doesn't work. The mouse is now making it move when it shouldn't. So no, it's making it move. So listen, I just won't use the mouse, okay? Otherwise, okay, I won't use the mouse. So the bottom here. So what I mean is Born rule unstable. What I mean is an initial state where you have the Born rule can evolve into a state where the Born rule is violated. So that's the sort of gist of what I'm going to be talking about. So the first point, no such thing as the Born rule in quantum gravity. The idea that mod psi squared is not a probability. Why can it not be a probability? Essentially because solutions of the Wheeler-DeWitt equation are non-normalizable. So psi squared cannot define a proper physical probability density. Why are they non-normalizable? Because the Wheeler-DeWitt equation is mathematically, its structure is like a Klein-Gordon equation. So for those who know about these things, so the DeWitt metric on superspace is indefinite. And so there is a mathematical parallel between the Wheeler-DeWitt equation and the Klein-Gordon equation on space-time. So because of this, if you try to normalize the Wheeler-DeWitt wave function, it's like trying to normalize a solution of the Klein-Gordon equation on the whole of space-time. Okay, that clearly cannot be done. If I integrate over t, I'll get infinity. Let's illustrate this with a model of quantum cosmology. Let's say I have a flat expanding universe, I have a scale factor, and a homogeneous matter field with some potential. So I'm looking at a mini superspace model with 2 degrees of freedom. So the Wheeler-DeWitt equation looks like this, with some choice of operator ordering. Notice, of course, there's no time. It's a wave function on this 2-dimensional mini superspace defined by A and phi. If I change variables to alpha as log A, where A is the scale factor, I get a Klein-Gordon equation with a potential term. Now, if you look at so I have this Klein-Gordon equation with a potential term. The free part has a general solution that, of course, we know is just a wave packet traveling in different directions. Notice there's no t here. These are traveling in quotes. This is just in this 2-dimensional configuration space. Clearly, a solution of this equation is not going to be normalizable in general. Okay, so this is why, because in this simple model, you see something that's actually quite general. The Wheeler-DeWitt equation has a Klein-Gordon-like structure. So it's solutions. If you have a solution on configuration space of notice there's no t, you have a solution on configuration space, you can't normalize it. Okay. Sorry that here sometimes I've got just psi as a functional of the metric. It's understood there's a matter field in here. I should have mentioned. I mean, the Wheeler-DeWitt equation with a matter field, there's extra terms, extra Hamiltonian terms for the matter field. Sometimes I don't bother to write it down just to keep the equation simpler. Sorry, where was I? I've done this. Anyway, so now let's say we have a Wheeler-DeWitt equation with a 3 metric and a matter field. To say that is the probability is naive. Now, this is well known in quantum gravity circles. Here's some old reviews. There's a big book by Anderson that came out a few years ago called The Problem of Time in Quantum Gravity. The idea that could be a probability is often called the naive Schrödinger interpretation. I think a terminology that was introduced by Unruh and Wald. This is problematic not only because the probability density is timeless. You've got a probability that does not depend on time, and people have tried to find a way to work with that. There's a long literature on this, but in any case, it ultimately fails because it's not normalizable. Now, a common explanation is that in the quantum gravity literature is that, well, the reason this is not a probability is because time is hidden in some sense in the 3 metric. So for example, in quantum cosmology, there's quite a common approach would be to treat the scale factor as an effective time parameter. This is an approach that is widely followed, but it's still controversial. There are all kinds of issues. For example, here, what happens to time if the scale factor expands and then recontracts? Does time reverse again? There are people who think that, like, for example, DeWitt, Ravelli, many others who think that time emerges only in some kind of approximate regime and that this is the right way to think about time. But I think it's fair to say that it's still controversial. But what I wanted to say is that from their point of view, this is a good reason for thinking or for understanding why psi squared is not a probability. I'd like to offer a different explanation, that the reason psi squared is not the probability is because in the deep quantum gravity regime, there simply is no such thing as the Born rule. I'd like to suggest that we can talk about probabilities, normalizable probabilities on configuration space that evolve with time, but they're not tied to the Born rule. I'm saying that in the deep quantum gravity regime, let's just forget the Born rule. It's not like the ordinary quantum mechanics that we're used to with time-dependent wave functions. It's a different regime of physics. There's no Born rule. In fact, I'm going to claim that necessarily probabilities are always different from psi squared because a proper probability density must be normalized. Psi squared is not normalized, so they can never be equal. So in this sense, quantum gravity is in this perpetual state of what I call non-equilibrium. And in my view, this is the true significance of this non-normalizability. But now, to make sense of this, we need to look at a theory in which probabilities are not necessarily equal to psi squared. So we're going to look at the pilot wave theory of de Broglie and Bohm. When I say interpreted correctly, I mean, just listen to what I tell you. The Born rule, this is a long controversy. I mean, speaking seriously, a long controversy in de Broglie-Bohm theory about the status of the Born rule. My view is that the Born rule is not an axiom or law, but it's a state of statistical equilibrium analogous to classical thermal equilibrium. And I've been talking about this for a long time. So de Broglie-Bohm, let me just have a quick time check. So, okay, I've only done 10 minutes. All right, okay. So de Broglie-Bohm, so it actually goes back to 1927. This is the theory that Louis de Broglie presented at the 5th Solvay conference in 1927. It's the low energy pilot wave theory of a many body system of spinless particles. You have the usual Schrödinger equation in configuration space, and you have a guidance equation, the equation for trajectories, which is a velocity law. Basically, the velocity is proportional to the gradient of the phase. So you have a wave function that guides the motion of the system. And as shown in detail by Bohm in 1952, you get the same predictions as quantum mechanics if you assume that over an ensemble, the initial positions in configuration space are distributed according to the Born rule. And it turns out, as I'll show you from the dynamics, that if you assume that at the initial time, it remains true. So let's illustrate the ideas for one particle. Let's say for I've got the one particle Schrödinger equation, as we all know, implies a continuity equation for psi squared. In this theory, psi is a wave that guides the motion of a single system. It's not a probability wave. Fundamentally, psi has got nothing to do with probability. It's just mod psi is just the amplitude of the wave. And it so happens that mod psi squared obeys that equation, and there's a natural velocity field, grad S over m. And that's just standard quantum mechanics. In de Broglie's theory, you assume that there are actual particle trajectories following that velocity field. And let's now think about an ensemble of systems which each have the same wave function, but different starting positions, all following that velocity law. How will the distribution of particles evolve? Well, by construction, the distribution obeys this continuity equation. This continuity equation just states that I have an ensemble of particles following that velocity law. But interestingly enough, it's the same equation that is obeyed by psi squared. So we have a simple theorem that if p and psi squared are initially equal, they will remain equal. Okay, and of course, this same mathematics applies in a higher dimensional configuration space. If you like, for a general system, I've got this configuration. It could be the configuration of fields. I could be on a background curved space-time as long as it's globally hyperbolic. I foliate it by some hypersurfaces. I have a time parameter, I have a time-dependent Schrödinger equation. I can define a velocity law for the time evolution of the configuration. And similarly, by construction, the density rho here, sorry, before I was using P, now I'm using rho. So what happens when you recycle slides from different talks. But anyway, rho is the density, will obey a continuity equation, which is the same as the continuity equation for psi squared. And again, you have this simple theorem that if I begin with the Born rule, I stay with the Born rule. Okay, now let's look at the example of one particle. If I fire one particle at a two-slit screen, according to de Broglie-Bohm, there's a wave coming in and it guides the motion of the particle. The particle starts somewhere. You solve the equation of motion. dx by dt is the gradient of the phase, and you can calculate the trajectory. It ends up somewhere. In practice, you don't know where it starts. If it starts somewhere else, it'll land somewhere else. If I have an ensemble of particles coming in, or it could be one particle at a time, if you like. And if the particles start at different points, they will land at different points. Now, it's a simple theorem, as I just showed you, that if the incoming particles are distributed according to psi squared, the distribution at the backstop will be psi squared. And so if you assume that you have p as psi squared coming in, you get the usual interference pattern of the backstop. However, if the initial distribution is not psi squared, you will disagree with experiment. So for example, in principle, according to this theory, at least as I understand it, there's no reason why all of the particles could not start at the same point. Imagine if I have an ensemble, they happen to all start at or close to the same point, they would all land at or close to that point. There would be no interference pattern. Okay? That would be an extreme example of p not equal to psi squared. So the point about de Broglie-Bohm theory is that if you take it seriously, it tells you that quantum theory is a special case of a wider physics, which I'll be talking about a lot more next week at a colloquium here. Okay, but you may say, well, okay, that's fair enough, but whoops, but fair enough that you could, in principle, you could have p not equal to psi squared, but experimentally, we always find this quantum equilibrium distribution. So for example, if I prepare a particle in a box and I prepare the initial quantum state as a superposition of the first 16 energy modes with certain coefficients, and I measure the particle position, I find it somewhere. If I now repeat the same experiment with the same preparation, I find the particle somewhere else. If I do this many, many times and I plot a histogram of the results, this is what you get. If you do this experiment in Rio, you do it in London, you do it yesterday, you do it next week, you always find this distribution. Why? Now, the usual answer is, well, the Born rule is a fundamental law of physics. In all the textbooks, it's just a law of nature. That's why. According to de Broglie-Bohm, there's a different answer. Is that you can understand the Born rule as having arisen from a dynamical relaxation process. So let's look at that example. Here I'm just plotting psi squared. This is psi squared at the initial time. And then I let psi evolve by the Schrödinger equation. You plot psi squared and it sloshes around. And it's a periodic system. So psi squared recurs after a certain time. It comes back to its original t. This is just the time evolution of psi squared. Now, normally we say, well, the initial density is psi squared, and that's the actual probability density. In this theory, I can say, no, I can begin with a density that is different from psi squared. So what I have here at the bottom is I have an ensemble of particles in the box with a cos squared distribution of initial points. each particle is guided by that wave function up there, superposition of 16 modes. And you can follow the time evolution of each particle, which, by the way, you know, this is a sample of this is a trajectory starting at the center of the box. You can see they're quite erratic. Anyway, you follow the motion of each particle and you can calculate the time evolution of the distribution. And you find that just over one time period, you get a very close agreement or relaxation towards psi squared. Now, I should point out that there is some coarse graining in these plots. One can quantify relaxation with the coarse-grained H function, which looks like this, which obeys an H theorem. Assuming there's no initial fine-grained structure, one can develop a sort of theory of relaxation. It's broadly analogous to the discussion that Gibbs famously gave of thermal relaxation in phase space. The kind of Gibbs approach to thermal relaxation in phase space. There's a similar kind of formalism that one can develop here. Numerical simulations show an exponential decay of this H. So this H function, by the way, is just minus the relative entropy of the coarse-grained density relative to the coarse-grained psi squared. The simulations show an exponential decay. There's a plot of log H versus T. Other simulation, this is a similar simulation done in a 2D oscillator. Just to confuse you, this time is going downwards. So here, up there, we begin, this is psi squared. So the initial wave function is a superposition of 25 energy states. That's a plot of psi squared, and it evolves with time. The units and the vertical axis change a bit. That's why it looks a bit. But anyway, this is going down. We start off with initial density that is a Gaussian. Okay, so that is the density rho. That is psi squared. Very different. As you evolve the density, you find that you get this very rapid relaxation. Again, the coarse-grained H function, here I've plotted H against T as approximate exponential decay, and so on and so forth. When would this process have happened? We're saying that the Born rule we see in the lab today is not a fundamental law. It's a bit like a thermal equilibrium state, except there's a bit difference in configuration space, different dynamics, but roughly, heuristically, it's a bit like thermal relaxation. When would this have happened? If you think about this, all the systems that we see, that we experiment with, they have a long and complex history. Sorry? Oh, is there a question? Oh, sorry. So this is just a two-dimensional oscillator. Periodic boundary conditions. So the 2D oscillator, this is just a non-relativistic 2D oscillator, and I have no. It's in a harmonic oscillator potential. And what you have is I have a superposition of the first 25 energy states. So the energy states, I mean, they go to zero at infinity. It's just because it's a bound system. So what happens is in principle, this goes out to infinity. It's just the tails are extremely small. And what happens, we consider a finite area because outside of that region, psi squared is so small, it's just negligible. So, I mean, this is a bound system. Sorry, I mean, before I was talking about the 2D box, where you have, you know, the 2D box, you impose that psi is zero at the edge of the box. But here, this is just the 2D oscillator. So it's a bound state and a harmonic oscillator potential. The tails go to zero. Okay, so if you think about this, well, when could this process have happened? It couldn't have happened this morning because the particles that we have in the lab that you experimented with this morning had been knocking around with other things the day before and the day before for millions of years. So if you think about this, if something like this did happen, it must have happened a long time ago, presumably in the very early universe, soon after the Big Bang. So if you follow that line of thought, it says that in effect you conclude that quantum noise is a relic of the Big Bang. Now, we know that CMB anisotropies, well, sorry, we know. According to inflationary cosmology, which may or may not be true, but anyway, according to inflationary cosmology, CMB anisotropies are ultimately generated by early Born rule fluctuations in the inflaton field in an early inflationary vacuum. So it's possible that if there were corrections to the Born rule in the very early universe, you would have a knock-on effect on the statistics of the CMB sky. I have a series of papers, this would be a subject for another talk, but a series of papers in PhysRevD about this. The last paper, there was some comparison with data, some intriguing hints, nothing concrete but or solid, but some hints. Anyway, that's one line of thought. What I'd like you to, so that's my little, the way I look at the Broglie-Bohm. The key point, the key message I like to get across here is that if you take the Broglie-Bohm theory seriously, it is telling you that the Born, again, as I interpret it, that the Born rule is not a law of nature. It holds only because we're in this quantum equilibrium state, which raises a question. Once we're in equilibrium, is there any way out? Now, the way I look at this is a little bit like, if you may remember, that in the late 19th century, people started to worry about the heat death of the universe. That from the understanding of thermodynamics, you could deduce, even without knowing much about how stars, what powered the stars, but you could deduce that the universe was in a certain sense running down, and that eventually everything would reach the same temperature. It was called the classical thermodynamic heat death of the universe. According to the Broglie-Bohm theory, a microscopic analog of that has already happened. We're living in a state of what I call quantum death, where there is a universal quantum noise given by the Born rule. We think that is fundamental because it's all we ever know, it's all we've ever seen. But my claim is it's not fundamental. It is a particular state of equilibrium that we happen to be stuck in. And the question is there a way to escape? Now, you might think, well, maybe we can create non-equilibrium. Let's go in the lab, let's take some atoms that obey the Born rule. Maybe if we hit them hard or if we smash particles together very hard in a high energy accelerator, can we create non-equilibrium? According to the de Broglie-Bohm theory, at least on a background classical space-time, P is psi squared is preserved by the dynamics. There doesn't seem to be any way out of this, except possibly very rare fluctuations. But that's like waiting for the oceans to boil. Okay, so if we leave that aside, there's no way out unless gravity changes the game. I have to speed up here. This is all Nelson's fault. Nelson, is your fault. You robbed me of 10 minutes. Anyway, okay. Where was I? Okay. So the question is, so I've given you this idea that, look, we're stuck in this state of quantum death. There seems to be no way out. But let's look at gravity. Maybe gravity changes things. Okay, so let's look at pilot wave quantum gravity. Really started in the early 90s. I put Nelson's review article 2021. Nelson and collaborators last 25 years has been the main driver of this work. If I was going to cite all of Nelson's papers since the late 90s, all that white space would be full. So I've just cited this review article that he has published in Universe in 2021. I'm going to be looking more mini superspace models, so I'd be a bit sketchy with the general formalism. But the Wheeler-DeWitt equation, and again, I've left off matter terms. There's also a momentum constraint on the wave function, which I won't bother to write down. But let's focus on the guidance equation for the 3 metric that looks like this, which you can get by putting the canonical momentum equal to a phase gradient. This defines the dynamics of a single system. Okay, I've got a Wheeler-DeWitt wave functional that is guiding the 3 metric in superspace. You've got the dynamics of a single system. But there is a question, is how can we construct the theory of a quantum equilibrium ensemble? Now, there's a funny situation here, because ironically, If you look at textbook quantum mechanics, you've got a theory of ensembles and probabilities, but there are no trajectories. There's no theory of an individual system. Okay, it's a theory of statistic probabilities. In the de Broglie-Bohm pilot wave quantum gravity that has been developed over these decades, you have the opposite situation. There's a lot of work has been done on the properties of the trajectories and singularity avoidance and all these interesting things. But there's no theory of probabilities and ensembles. And the reason is because, well, chi-squared is not normalizable. So it's sort of opposite to the situation in the textbooks. But now, but what I'd say is that what we do need a theory. We do need to be able to discuss probabilities and ensembles. So how can we do it? So here has been my suggestion that for a general ensemble, let's take the dynamics of a single system as written down. Again, I've left off the momentum constraint. And what we're going to say is that an arbitrary ensemble with distribution P will evolve by this continuity equation, which simply states I've got an ensemble of three metrics, each guided by the same wave function, so they follow that velocity field. And this just states, it's just a continuity equation that just states that these three metrics are following that velocity field, where the distribution P is assumed to be normalizable, so it cannot be chi-squared, and it will evolve in accordance with this general equation. And the claim is that, well, this theory has no equilibrium state. Unlike the usual de Broglie-Bohm, where things tend to relax to chi-squared equilibrium, this theory, there is no equilibrium state. Now, let me illustrate with the model of quantum cosmology that I wrote down earlier. If you do the usual polar decomposition, you get this, what I call a pseudo continuity equation, but there's a preserved density. The non-normalized, the Born rule, because of the structure of the configuration space here, instead of the chi-squared Born rule, the usual Born rule is actually a squared chi-squared. There's a factor of a squared. But it's still non-normalizable. The de Broglie velocities that you get by putting canonical momentum as phase gradient look like this, okay? Now, and again, normally there is this problem. Well, how do I discuss probabilities? A squared chi-squared can't be a probability density, is not normalizable. What do I do? So people just focus on trajectories, they calculate trajectories, they never talk about probability. I claim that you can talk about probabilities, that a general probability density will evolve by this equation. It's just got an ensemble, a finite ensemble of systems with that velocity field. It will evolve by that equation. Now, at this point, we should be aware of the naive Schrödinger interpretation coming back to haunt us, because P and A squared chi-squared obey the same equations. There's no T in the second equation because psi is time independent, but really there's a d by dt here, it's just zero. These are the same equations. You might think, well, I have a state of quantum equilibrium. But no, that cannot be, because P by construction must be normalizable. A squared chi-squared is not normalizable, okay? So we must have P not equal to the Born rule always. If I take this continuity equation, I evolve forward in time. Equilibrium can never be reached. Now, I have actually done some simulations with a former student, Aditya Kandhadai, which our paper is not quite finished, but basically I can report that numerical simulations analogous to ones that I showed you earlier for the oscillator and the box, if you do it for this mini superspace quantum cosmology, and you see what happens to we start off with a little Gaussian distribution of probabilities. It evolves, does it start to look like A squared chi-squared? No, it doesn't. There's no relaxation. Formally, the coarse-grained H function, when there's an A squared missing there. How could I do this? Sorry, there's an A, instead of A, it should be A squared. Anyway, because A squared chi-squared, the target density is not normalizable. This H function has no lower bound. You could think of it that way if you like, that this system, the H function decreases, but there's no lower bound. In any case, these simulations illustrate this idea that quantum gravity is in perpetual non-equilibrium. Okay, now let's move on. Implications. Okay, so the Born rule But then there's a problem. You might think, well, there's a problem. Hang on, if I don't have the Born rule fundamentally, where do I get the Born rule that we see in the lab? Actually, there's no problem, because in the semi-classical regime where I have a time-dependent Schrödinger equation, you can still get relaxation of the form that I showed you earlier. So how does this happen? Semi-classical approximation to the Wheeler-DeWitt equation. I'm going to have to sort of skip over but you can derive an effective time-dependent wave function for the quantum field. Here you take the, so remember there's no T up there, but what you do is you have the Gij as an approximately classical solution for the background that depends on time. And so I define an effective time-dependent wave function for the quantum field, which obeys an effective Schrödinger equation. For instance, if you look at Kiefer and Singh, 1991, for instance, don't go through all this in great detail, you get an effective time-dependent Schrödinger equation with an effective Hamiltonian for a quantum field on a classical background. And now, the psi, the effective psi, is now normalizable. And so you can get relaxation now, as, you know, for example, here, the example of the 2D box I showed you, but you'll get a similar kind of relaxation for the modes of a quantum field on this background space-time. Note, however, because fundamentally, in the deep quantum gravity regime, the parent probability distribution can never be equal to psi squared, the initial conditional density for this field will be out of equilibrium. You will begin out of equilibrium. And so the idea is, well, the deep quantum gravity regime, there's no such thing as the Born rule. As you enter the semi-classical regime, you have non-equilibrium, and then you can have relaxation. Okay, but then you might think, well, okay, so we're still going to be stuck in quantum death. Relaxation is going to still take place in the semi-classical regime. Once you reach the Born rule, we'll be stuck there forever. So we're still stuck with the Born rule. Well, perhaps not, because maybe gravity changes the game. In the tiny quantum gravitational corrections to the Schrödinger equation could make the Born rule unstable. So here is the point that people for decades have studied higher order semi-classical expansion and have found small non-Hermitian terms in the effective Hamiltonian, which is of course inconsistent with standard quantum mechanics. In de Broglie-Bohm or pilot wave theory, non-Hermitian terms generate a small instability of the Born rule. Let me show you how this goes. So non-Hermitian corrections. A series of papers on this, just a couple of references. This is sort of what it looks like. Here is your effective Schrödinger equation for a scalar field on a classical space-time background. You get the standard Hamiltonians corrected by a Hermitian term and a non-Hermitian term. There are powers of the Planck mass in here. These corrections are extremely tiny. So experimentalists don't get excited. They're going to go and look for them in the lab. I mean, they're extremely tiny. But anyway, I should also mention that the people who have derived these terms, you know, they're not quite sure what to do with them because they're inconsistent with standard quantum mechanics. So in some papers, people, for example, redefine the wave function in such a way as to eliminate the non-Hermitian term. And there is a question there. Are you eliminating some artifact, and that's the right thing to do, or are you actually artificially eliminating something that is physically there? The point is that in de Broglie-Bohm, you can make sense of these terms. So people who want to know how did this come about, just this is a quick peek at the paper by Kiefer and Singh. There's a semi-classical expansion of the Wheeler-DeWitt equation and the corrected Schrödinger equation. Look, this is their general result from that paper. This is what these corrections look like. And as you see, the non-Hermitian term, there's a factor I there. Okay. Let us look at pilot wave theory with the non-Hermitian terms. So let's take it that a semi-classical expansion of the Wheeler-DeWitt equation gives this result. An effective Schrödinger equation with a Hermitian and a very small non-Hermitian part. Let's now look at the semi-classical expansion of the de Broglie equation. So basically, this same semi-classical expansion we can apply to the de Broglie velocity for the scalar field. And this is some work that I did in those two papers that I mentioned. What you find is that the velocity field, in other words, the phi dot, the time rate of change of this scalar field, is not affected. It's just the standard expression in terms of the new effective wave function. So you have this interesting situation that now the density rho evolves in accordance with the usual velocity field, and you have this, by construction, that continuity equation, but psi squared obeys a continuity equation with a source term. So now where the source depends on this H2, which comes from the non-Hermitian part of the effective Hamiltonian. Now the two continuity equations do not match, so an initial Born rule is no longer preserved in time. It evolves to non-Born rule on a time scale that you can estimate. Could such effects be observed? So, okay, I should be able to finish in 5 minutes, so at least we'll have 5 minutes for questions. I hope that's all right. So could such effects be observed? So quickly, cosmology in the CMB. Again, these papers by Kiefer have studied the effective Schrödinger equation for scalar perturbations on de Sitter space, also with slow roll in a follow-up paper. Anyway, this is an example of the sort of thing they find. You've got this is the first term there is just the usual Schrödinger equation for a mode of a scalar field on a background expanding space. These are the corrections. You've got the Hermitian part and the non-Hermitian part there. This is what it looks like. So HK is just the standard Hamiltonian for a scalar field on a background. So it's just P squared plus Q squared. Okay. And of course, they want to consider how do these correction terms affect predictions for the CMB. Now, understandably, they consider only the Hermitian term, because a non-Hermitian term, well, what do you do with it in quantum mechanics? And they find a tiny correction to the power spectrum of order 10 to the minus 10, far too small to see. There were similar papers earlier, Kiefer and Kramer, Beeney et al., looking at similar things, tiny corrections to the CMB power spectrum. In one of these papers, I did a similar kind of study, very approximately looking at the effect of the non-Hermitian term. It generates quantum non-equilibrium during inflation. If this kind of, if you take this kind of equation seriously, during inflation, it will generate corrections to the Born rule, but the effects are extremely small. And again, in a similar kind of order, there's no hope of seeing any of this in the CMB. What about an atom in the Earth's gravitational field? How about just putting an atom in the field? Would there be some small non-Hermitian corrections that maybe could build up over time? It may sound a bit silly, but actually, let me just go back to, if I can show you, in case you remember where this came from. Remember here, there is a time derivative here. This is the bubble time derivative on a hypersurface. So if I have a time-dependent Hamiltonian in a gravitational field, it turns out that if I have if I have an atom in the gravitational field of the Earth, and the Hamiltonian of the atom is changing with time, you get a small non-Hermitian term according to these. But the thing is, it's suppressed. You've got a Planck length divided by the radius of curvature at the surface of the Earth. There's a Planck time. If you estimate the time scale over which corrections to the Born rule will be generated, it's far, 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 far longer than the age of the universe. So that looks pretty hopeless too. What about evaporating black holes? Okay, just a couple of minutes and I'll be it. Again, following, so the paper, interesting paper by Kiefer, Muller, Singh, 94, they estimate that if I have, they've got an evaporating Schwarzschild black hole with a time-dependent mass that's just modeled phenomenologically. And they talk about a scalar field in that background space-time. And the claim is that the field mode for a scalar field will have a small non-Hermitian correction that looks like this. K is just a numerical factor. Well, the Planck mass divided by capital M is the mass of the black hole. So it's suppressed by the Planck mass divided by the mass of the black hole to the 4th power. And at that time, they were suggesting, because it's non-Hermitian, maybe it has something to do with information loss, but it's not very clear. If we do this with de Broglie-Bohm, it's saying that, well, in the background spacetime, the scalar field, if it begins in equilibrium, it will develop corrections to the Born rule on a time scale that you can estimate. The time scale looks like this. It goes as the mass of the hole divided by the Planck mass of power 5. If this is right, I mean, this is of course significant only when the mass approaches the Planck mass. So it's only when the final little burst. In principle, if you take this seriously, it looks as if the final little burst of Hawking radiation, if the black hole evaporates completely, could break the Born rule. Could such a thing be seen? Well, we don't have black holes in the lab, but people do search for exploding primordial black holes. The universe could be, there could be a large population of primordial black holes that were formed by density perturbations that collapsed in the early universe. If primordial black holes have a mass of, I think it's about 10 to the 15 grams, their lifetime is of order the age of the universe, so we could see them exploding now. And people search for this. You've got the Fermi gamma ray satellite, various satellites looking for this kind of thing. In principle, if we saw black hole explosions, we could subject the gamma rays to some sort of interference experiment to see, do they obey the Born rule? It so happens that there's this German satellite mission called QUIC to the power 3. Somewhere, I can't remember what the reason is for that. Anyway, this QUIC satellite is being launched next year. They have an interferometer on board for the purpose of testing the Born rule in space. And it's part of this sort of general program of testing quantum mechanics in space. Their satellite actually has an onboard photon source, but they're going to do experiments testing the Born rule in space. Once such a thing is up and running, if we did find gamma rays from exploding primordial black holes, well, then we could maybe let those photons come in and come into this interferometer, possibly something for the future to think about. The only issue here is that, as I said, the exploding primordial black hole is only the very final burst that you would expect to see significant deviations from the Born rule. Most of the radiation that you see is going to be from when the hole is much bigger. Will you be able to find this little thing, even if it's there? Will you be able to find it in this mess of radiation? Don't know. Conclusions. So remember the 3 points I wanted to make to you. One is that quantum gravity is fundamentally a non-equilibrium theory. There's no Born rule. 2, in the semi-classical regime, we find relaxation to the usual Born rule. So even though I've told you that fundamentally there's no Born rule in quantum gravity, we still get the Born rule empirically that we see in the lab in the regime where we need it. Okay. Thirdly, more controversially, assuming that these non-Hermitian corrections really are physical things and not artifacts, corrections to the semi-classical regime yield a very small instability of the Born rule, possibly, so the latter effects are very small, except possibly in final burst of an evaporating black hole. That's the talk. May I permit myself an advertisement, please? 30 seconds of your time, advertisement. I have 2 books going into production out next year. The first is aimed at advanced undergraduates, beginning graduate students. It's called Introduction to Quantum Foundations and Pilot Wave Theory. I also have a book for the general public called Beyond the Quantum. The subtitle is A Quest for the Origin and Hidden Meaning of Quantum Mechanics. So there you go, get your orders in early in time for Christmas next year. And that is it. Thank you very much.
Thank you so much for our lecture. Questions?
Thank you, Professor, for the lecture. I have a question. You said that we have these non-Hermitian Hamiltonian terms coming from the Wheeler-DeWitt equation, but Nelson showed us that he can solve the Wheeler-DeWitt equation using de Broglie-Bohm, and he doesn't have this kind of things.
Yes.
Why is that?
Okay, so if you're just looking at the Wheeler-DeWitt equation, so these terms arise when you do a semi-classical approximation, where I derive an effective time-dependent Schrödinger equation on a classical background. Well, actually, if you do that to the lowest order, you just get the usual Schrödinger equation for, say, a scalar field on a classical background. There's nothing on Hermitian. It's only when you look at higher orders in the semi-classical expansion, you derive correction terms to the Hamiltonian. You find both Hermitian and non-Hermitian terms. Now, the thing is, those terms are extremely small. You know, for most purposes, you know, you would just look at the usual Schrödinger equation. Unfortunately, I arrived very late at the conference. I had a late flight Monday night. I missed Nelson's talk, so I don't know. Maybe Nelson can. You know, for most applications, people don't consider. Basically, these non-Hermitian terms, they are quantum gravitational corrections to the effective Schrödinger equation. They're extremely tiny. So, you know, for most purposes, even the Hermitian part, the Hermitian correction, there's no point considering it, it's so small. So maybe that's why. In principle, you see what it would be. Maybe I can look at this sort of thing. For instance, here, this sort of thing that Kiefer and co do. This is the Schrödinger equation. This is for perturbations. I mean, this is really for the scalar field. Really, this is basically the Mukhanov-Sasaki variable. It's perturbation theory on an approximate de Sitter space. Okay, so this is the Schrödinger equation for perturbations. Now, these correction terms that come from higher order terms in the semi-classical expansion are extremely small. You know, for most purposes, you know, forget it. You've just got the. So presumably, I think Nelson, in the sort of work he's just got the first term on the right-hand side, which is the standard Schrödinger equation for perturbations on a background, and then you do the de Broglie-Bohm theory. So, you know, as you see, if you the Hermitian part, the correction to the power spectrum is fractionally order 10 to the minus 10. So, any other questions?
There is another question over here.
I have a question about the atomic system. That just a comment on that question. The way that Nelson does, first he does a canonical transformation, then he imposes some conditions on the solution, then he gets the solution. Here he starts by doing the semi-classical expansion and then plugging the semi-classical expansion, the Wheeler-DeWitt equation. Are two methods that are different, and maybe the corrections that he finds, he would find if he do another kind of solution, maybe, but not necessarily. And my question is, on this term here, you have HA, that's already the correction.
So sorry, HA is the atomic Hamiltonian. Sorry, I think on an earlier slide I used HA for something else. Here is HA is just the standard atomic Hamiltonian.
Yeah, it's the Hamiltonian in the sense of the system that you're measuring the relation of.
Say, for instance, I've got a hydrogen atom.
Yeah.
And it's in a time-dependent electric field or something.
So
okay, that's just the standard textbook Hamiltonian.
Yeah.
For the hydrogen atom. Yeah.
Let me ask you that. So if you have a system that's a little more complicated with a more complex Hamiltonian and time-dependent structure, this derivative might result in a correction that's might grow with time, that has a structure that's eventually, if we think of a system that oscillates very fast, that accelerates, that whatever.
I would hope that if some clever young guy comes along with an idea of how to make this, at first sight, I mean, all I've done, if you look in my paper, is I've got that time scale, which is a very rough estimate of the time scale. If you look at it and you just plug in kind of normal things you'd expect, you get this huge 10 to the massive number times the age of the universe. Is there some clever, more thoughtful way of making the effect significant? Maybe, I would hope so. But
So unfortunately, I have to stop with coffee break. So let's thank Professor Vitenti again.
Thank you. Thank you so much. Thank you. Okay.
And we'll be back at 10:30 sharp.
Okay. So, okay, I got it. Ah, yes.
Don't you have a complex energy in the case of Hamiltonian, non-Hermitian Hamiltonian,
Mm.
people gamma vectors?
Uh-huh.
Maybe.
I hadn't thought about that. You see, the thing is, the non-Hermitian terms are so tiny that you sort of treat them as very small perturbations. So, you say, well, what system am I talking about? I've got this system with these energy level by the usual Hamiltonian. Then you've got this
Hi, welcome back from coffee break. Now we have the second lecture of the day by Vittorio De Laurenti, exploring aspects of chronology protection in non-trivial spacetimes. Thank you, Vittorio.
Thank you. Good morning, everybody. First of all, I'd like to thank you, Mario, for the invitation. It's always a pleasure to be back home. It's DPF. And in this seminar, I will explore some aspects about the chronology protection conjecture. And by non-trivial space-time, I mean locally flat space-time. And the idea is to provide an example in which you can verify this protection conjecture. I will start with this sentence. It was published in a paper in 1992 by Hawking. This paper appeared as a consequence of a series of discussions in the scientific community about the relativity that presents a closed time-like curve. So as you know, a closed time-like curve is a sort of entrance for a time machine. And well, in the words of Hawking, it seems that there is a chronology protection agency which prevents the appearance of closed time-like curves and so makes the universe safe for historians. Well, I select a couple of papers in which this aspect, this classical aspect of the existence of closed time-like curves appear in the literature. This one is perhaps the most famous one from Morris Thorne and Woodsever. In fact, this paper particularly appeared as a follow-up contact of Carl Sagan. In that time, he was writing a novel, and he would like to know a possible scientific mechanism to send one of his personages, Eleanor, to Vega about 26 light years and back in a short time. So the second paper of after this contact, in fact, Carl Sagan appears in the acknowledgement of this paper. But the main idea of this paper perhaps can be summarized in this figure. The idea here is to use a wormhole to generate a possible device to time travel. In this picture here, you have a wormhole. This is the left mouth of the wormhole, this right mouth. And so they explore the consequence of sending the two mouths of a wormhole in a twin paradox. So suppose here we have the laboratory when you keep the left mouth, and so you put the other one in motion like that in this space-time diagram. And the problems appear just after instant time of between 8 and 9. For instance, if you enter the mouth, the right mouth in this instant 12, so you arrive here. And so when you arrive here, you can take a way, a subluminal way, of course, in order to get there just in time to avoid yourself to enter the mouth. So all the logical paradoxes that arise from this kind of problem appear here. This perhaps the most famous paper about this topic, but there are other ones. I select other two. This one is from Frolov and Novikov. They explore about the same thing, but in a different way. They show that interaction of wormhole with surrounding matter and with gravitational, external gravitational fields leads to time machine device too. Okay, it's another possibility. The last one I mentioned here, there are a lot of them, but this last one I mentioned here is a paper from Gott. Here, he shows that when you have two straight cosmic string in relative motion, you also produce CTCs, closed time-like curves. Okay. So in a more strong way, this appears in the Hawking paper, the abstract Hawking paper. The laws of physics do not allow the appearance of closed time-like curves. This is conjecture. So he explored this idea in a very general way in his paper by examining the evolution of a Cauchy surface until it gets a situation in which you have a problem with the global hyperbolicity of space-time. The idea of the seminar is to explore in a certain scenario this idea and show that the quantum mechanics provides such agency to prevent causality violation. Okay. Well, it's funny to note that Hawking proposed an experiment in 29. He proposed he hosted a reception of time travelers, and the idea is that he published this invitation only after the party finished. So nobody would know about this party, but only the future. So, but needless to say that nobody appeared. Okay, so there are other principles, not so rigorous about not so strong, I would say, about this problem. This one, for instance, is related to a series of works, in fact, even papers from Kip Thorne, about the possibility of having such special curves, closed time-like curves, but in such a way that you could, in fact, produce ways to the past. But, well, it's better to read here. It's a better way to understand this self-consistent principle. If an event exists that would give rise to a paradox or to any change to the past whatsoever, then the probability of that event is 0. I will just show you these 2 possibilities here just to sum up the contents of this self-consistence principle. In the first panel here, we have the Polchinski paradox, which is, of course, a logic paradox. We have a billiard ball game in a table in which you have this mouth here is a mouth of wormhole that leads something that enters here to the other mouth, in which it comes out in a certain way that it will interact with itself just before enter the mouth. So the Polchinski paradox is like the grandfather paradox. So if you send a ball, for instance, in this mouth and return, interact with itself again in such a way that it deviates from the entrance. So you have all these things that appear in the space-time, like a violation of energy conservation law and other things. So if it didn't enter, so how could it have meet itself in the past? So if you use the self-consistent paradox, so the solution to that would be disappear in the paper, PRD paper 2, Kilveria, King-Hammer, and Kip Thorne. The solution for using the self-consistent principle would be that, okay, you have wormhole, and you can accept the ideas of general relativity as only a classical theory, and you could go to the past, but interaction that you can have with itself occurs in such a way that it will not modify the fact that it entered this mouth here before. So you avoid the global puzzles about, for instance, energy conservation, other things. Only local problems would appear here. Okay, but this is just literature about that. This I will not explore in details, but I would like just provide an example in which you can show that quantum mechanics prevents is such agents that can prevent the appearance of closed time-like curves. That's the idea of the seminar. Okay, so let me introduce the idea of cosmic strings, if you don't know, but I think everybody knows, but just to set notations. These are objects that are solutions of Isaacs equations, and that's enough to me, okay? Because I will use that as a laboratory to test these ideas about Hawking's chronological protection. Okay, but anyway, it's also predict to be produced in a very early universe, like a phase transition, that you can find out when the water freezes, for instance, if you produce. In fact, I went to the literature in order to find out some papers where this event occurs. This is a possible example. There are several ones. These are analog of the process that occurs in the very early universe in terms of phase transitions. If you drop, for instance, water in a platform that is very cold, here, these 2 last ones here is about 50 to 60 degrees gradient of temperature. So it suffers a very sharp phase transition and all these defects appears. It's a very interesting to show that. The papers that talk about cosmic strings in context of grand unified theories always compare this event with such things. It's like war freezing. Very sharp. Okay. Here is another possibility to see this kind of process in phase transitions, which occurs in liquid crystals. It's better to see here because you can evolve the system and see what is happening. Like in this case here about the instant 33, the phase transitions occurs, and so you get all these defects, etc. But about this instant here, you see that two defects approach each other, and so they will cross, and so it will form configurations like that, which are known in terms of cosmic string as cusps and kinks and things like that. So they interact, they can form loops. And the people who condensed matter system are not specialists in that area, of course, but people from condensed matter systems usually say that they can produce all kinds of interaction that people from cosmology say about the interaction of cosmic strings in laboratories. So just analog models, okay? Here I gave just an example that I got in the literature about this kind of interaction. Here, interaction between two cosmic strings, and this interaction of a cosmic string that interacts with itself. So it can produce loops and kinks and other things. Okay. So in terms of general relativity solution, this is space-time of a cosmic string. So we have the defect, I call it a defect, an angular defect. The presence of this cosmic string appear encompassed by this parameter here. You can relate this parameter with the mass density of the string, which can be constrained in some of these recent experiments, like LIGO, for instance. It's a very large number, in fact. Mu is a very large number, but this guy here is C mu over C squared. So if you do the calculation, use the possible values for mu, predicted values, you get something like 10 to minus perhaps 12 or things like that. So it's a conical space, but a very shallow cone, in fact. Okay, so but in terms of Einstein's equations, solution of Einstein's equations, this parameter alpha could also be larger than 1. Usually it's assumed to be less than 1 if these guys exist in nature, which is an angular deficit, but you could also have solutions for alpha bigger than 1, which would be an angular excess. If you write that in terms of flat coordinates, so I could define this angle theta, which is alpha phi, and so have Minkowski metric written in symmetrical coordinates, but now theta goes from 0 to 2 pi alpha, so have a deficit angle there. Okay, so you can exchange the presence. You can exchange this method by this one, but you need to remind that you have a new identification here to this parameter theta. So you need to take that in consideration and you calculate things with fields and other things. Okay, here it's a recent physical review letters from LIGO where they constrain the possible values of these guys if they exist to this value here, G mu over C squared, this size. Okay, let me return again to the condensed matter systems because I'd like to work with a little bit more general solution, also solution of Einstein's equations, okay, which generalize the concept of a cosmic string. Okay, so just to introduce the idea, they have also analog, three-dimensional analog of this kind of solution in crystals. So they can produce that in condensed matter, but just by removing a slice of a cylindrical symmetric shaped crystal like that. And so you can glue using a perfect glue the two face like here. And so all the strains and stress that can produce that will be encompassed in this new parameter, which is exactly the three-dimensional sector of the S squared of a cosmic string. Okay, and if we can go further and produce a defect like that, condensed matter systems call this defect as a dispersion. The analog of cosmic string is called as disclination, which is a new word in the vocabulary about that, in fact. Because the correct word initially would be disinclination. Well, it's another thing. Let me go ahead. Okay, so in this case, you can do the same thing. Remove a slice of the crystal, and so when you wish to glue these two faces, you can do that as before. But now we introduce a new defect by sliding this face here up and the other down. For instance, when you glue the face together, so you produce a defect in the lattice of the crystal, which will produce something like a helical symmetry. So when you do that, in terms of crystals, you can encompass these two kinds of defects: alpha by the disclination defect, with this one here by the dislocation factor. It's related to the Burger vector, if you studied that in the undergraduate studies. And now you have a dispersion. They call that a dispersion. So the question is, do you have this kind of solution in general relativity? I mean, in terms of space-time? The answer is yes. I will tell you after. This is just to show you an application in crystals. These are a crystal of silicon carbide that was grown from an initial defect of this kind. Okay, so now I return to space-time. So yeah, the answer is yes. You have, this is also a locally flat solution of Ison's equations, exact solution, which now have a cosmic string here as a particular solution. We have kappa is equal to 0. And you know that, you see that you have a coupling between Z and phi coordinates now. This solution was discussed together with many others by Galtsov and Letellier in 1993. And they explored the ideas of getting the solutions that you have in condensed matter systems. They call the Volterra distortions. I think they are there, 10 distortions that you can produce in a crystal, perhaps 10 or a little bit less. But in fact, you can also have solutions of Ison's equations. These are locally flat solutions, exactly locally flat solutions, in which you can have analogs in condensed matter systems. So this one is the one that I would like to use in the seminar, and also this one here, which is the solution for a spinning cosmic string. So for a spinning cosmic string is very tricky solution, because here you can produce CTCs. So if you wish to do physics in this space-time, you need to take care about the details in order to avoid causality violation or all the things that come together with that. Okay. The first aspect that I'd like to discuss is about what kind of effects that will arise in a space-time that have these two defects here, alpha and kappa, excess or dash angle, and a dislocation in this direction. Okay, so the first idea is to calculate the self-force, self-interaction. So I have a particle. Now the space is no more impulsive space. So I have a kind of conical space. So if you think about the force lines that the particle produces, it could be a charged particle or just a point mass. Okay, so you could produce a gravitational potential, for instance. So have the line force that spread to infinity when you have Minkowski. But if you have a conical space, you can think that something more will occur, because the lines will perhaps meet, well, approach each other in the other side. But in terms of particle, it seems that there is no problem. But fields will receive the whole space. So in fact, if you calculate that using the usual method, you can find that there is some new things here. Here's the usual method that you use in electromagnetism. So the idea is to solve this equation here for the potential, in this case, the gravitational potential. So it's a particle of mass m is located in R prime. And so you do the usual math in order to calculate that. So you solve the equation for the Green function, and so you can obtain the gravitational potential in terms of the limit of point coincidence of the Green function, so you can calculate the force. Okay, so is there any fact that arises from that? Yes. Well, I can skip that. Yes, you have effects about the presence of these two effects, the kappa and alpha effect. This is the solution that you can find out after some calculations. So it's gravitational potential. Okay, so you have this function here that you can write in this way. Okay, so you have the alpha parameter here, and here, and kappa is there. Okay, this location. If you put alpha is equal to 1, no dashed angle, no ordinary quadratic string, and kappa is equal to 0, so no dislocation, so you have just Minkowski space, and the solution is just 0 and have no effect at all. Okay, but when you consider these two effects, you can produce this kind of behavior. Here, for instance, if you have alpha is equal to 1, so just dislocation space. So it depends on the value of kappa. Here, B is just 2 pi kappa. I wrote B here because in principle, you were made a connection with condensed matter systems. So they used the notation for the Burger vector. So B would be for Burger vector, the intensity of Burger vector, which relate to the defect in the crystal, for instance. But here is just kappa dislocations. And so there is no elaborate things occurring here when you have alpha is equal to 1. And also when you have an excess angle, the solutions are quite safe. I mean, the behavior is quite safe. So we have a potential barrier. So some new quality appear when you have a trade-off between alpha and B. So if you have a alpha dashed angle and B is different from 0, I mean, you have dislocation too. So the trade-off between these two defects will produce, for instance, bound solutions. It is very interesting. The solution for B is equal to 0, this one here, was already discussed by Smith in these proceedings here. I think Smith was a PhD student of Vilenkin at Tufts. Isn't it? Yeah. Okay. Okay, so this is the classical aspects. So we have classical self-force that comes from the presence of these two defects. And so it can lead to new solutions like that. And the next question now is, what about quantum mechanics? So initially you do quantum mechanics this space-time. So I have this space-time with alpha and kappa, so I have dislocation alpha. It's all safe to say to do quantum mechanics because we don't have problems with the global hyperbolics of the space-time. It will occur only when you have a CTC. It's not the case, okay? So I have the solution there. If I write it in flat coordinates, so I can just work with this metric, but remembering that theta and psi would be identified like that. So the fields would be to be identified. I need to provide the identification of these coordinates when I derive source for the equation motion. So the idea here is to calculate the propagator. In this case, I calculate the Feynman propagator, the usual method. I'll not go into details about the math, about this things, but just remember that when you calculate that, when you solve this equation, we need to observe this identification here. Okay, so this identification, this in fact is the boundary conditions that you usually do, okay? But it's the identification that brings to the problem the presence of the defect. So this is standard recipe to calculate this. So the solutions are that. So you can find out this renormalized green function, define the propagator, and so you can calculate your observables like this phi squared, the mean squared, the vacuum expectation value of phi squared. You can calculate by using this solution. I will show you some plots about that. And here appear the energy moment tensor, which would activate gravity too. So this is one point important here. Okay. So these are the dispersions. Okay, it's just to mention that the solution is not so difficult. This F function is the same one that appeared there when you calculate self-force in the classical domain. Okay, so here we have two limits in which you obtain a very neat expressions for phi square. So, but in order to study the general behavior of this solution, needs to go numerically, and so we obtain these solutions here. So as before, the interesting effects appear when you have a dash triangle and a dislocation together. Otherwise, you have just this behaviors, simple behaviors. So just to select one case here for a dash triangle of like that, 0.75, which is just numbers. Because I'm not really interested in the numbers behind that, because I'm just using a laboratory to test some ideas, okay? But if you're interested in the magnitude of defects, I can show to you later this information in the papers. That's because I didn't put here this scale effect. Okay. So what about the expectation value of the energy moment tensor? So you can calculate that too. So we obtain this expression here for the vector expectation value of the energy moment tensor, and you see that you have now some off-diagonal components that appear because of kappa. So this, the presence of dislocation brings new things in the quantum description of this effect here. So okay, so now, now we get the point about gravity, because you quantize a field in a space-time which is locally flat. Okay, so you get some energy moment, some extra energy moment tensor, but this guy also curved the space, so we need to be back and see the consistency of that here. Okay, so this connection is summarized by the name back reaction. So this is the back reaction scheme that I'd like to explore from now on, and the general okay. The general things here is the following. We start with Ison's equations. So we have a solution of Ison's equations like the one that I used before. You have alpha and kappa, okay? So in this non-trivial space-time, it's locally flat, but non-trivial. So we can quantize fields. This is a scenario of quantum field theory in curved space-time. Okay, so but when you do that, you produce a new ingredient here of energy. So you need to be back to Ison's equations and see this again. And so calculate the back react metric. And so you have a scenario in which you can talk about consistency of your model by means of the back react terms. And so you need to compare it and stay in a level that you can really say that you have something new, because the point here, the breakdown of this scheme is when you be back, you get back this metric in the original equations, and so see that the correction will be of higher order. Okay, so this is the main scheme about that. Okay, so yeah. Sorry, I use conformal coupling for this kind of case. Let me see if I mentioned this here. There. Yeah, sorry about the name. This is the same name I used for the coordinates there, but it just appeared here, so forget about that. Yeah, but thank you. It's a conformal coupling field. Okay, so this is just to see a possible application, a possible consequence of that. So we calculated the acceleration, the contribution to the acceleration of a particle in this space-time. We have just a cosmic string with a dislocation. So calculate there what would be the motion of this particle in this space-time. So you get the three components of the acceleration, and you can examine some consequence here. The first one is the following. Suppose that you have the particle that put there initially at rest in the space-time. So we have here a component that's always active. You see? There is this quantity here, which is a function of the parameter alpha, and here you have 1. Okay, so if initially these guys are 0, and also this one, don't worry, this is 0 or not. In fact, we'll also always have acceleration in the radial direction. So the particle will start moving in the radial direction. It will be approach or going far away from the defect. But here, for theta and psi, we have a coupling between these two velocities, rho and psi, and here rho and theta. So it will be always 0, and there will be motion only in the radial direction. However, if you start with v theta different from 0, you can see that this guy will be active. So just after you start the motion with this initial condition, we activate v rho, which is here, you see? So you activate acceleration in z direction, but when you do that, you activate also v psi, and so activate the acceleration in theta direction. So the presence of the kappa defect dislocation will produce a motion like that. It will take the particle away from a planar motion and to be a kind of helical spiral motion like that. Okay. Now we arrive to the main point of this presentation. It's about the presence of closed time-like curves. So when you have a space-time like that, it's very simple to see that if you could find you could set a section like t, rho, and z constant. So the s squared, which is invariant, is just s squared minus alpha squared, rho squared, d phi squared. So here is phi, so phi can go from 0 to 2 pi, so do a complete turn. So, and with d s squared is greater than 0, so it's a possible solution. And it's a closed time-like curve. Okay, it is a CTC. So space-time with a spinning cosmic string always presents CTC. So it's a big problem for instance, to do quantum field theory in this space-time, because you don't have a global Cauchy surface in order to evolve data. So all the puzzles about that in quantization of fields appear, but there are some possibilities to work in this kind of space-time. For instance, I would mention here NAMI is writing collaborators that consider, for instance, the quantization of field in this space-time, but avoiding the region in which you have this problem about the global hyperbolicity of the space, just setting a boundary condition in order to avoid this region of causality violation. So that there are some possibilities to work there. Okay, but let me go ahead. As I mentioned before, when you have a CTC in your space-time, this is just an entrance to produce time machines. This is a very simple way to see that there's a CTC here, but you can elaborate that and produce something like that. You can set a curve in which rho and z is equal to constant. So if you choose dt and d phi is more than 0, so you can start, for instance, this point, and as you go to your future, you are going just approach your past in this way. You can arrive here in the same points in terms of rho, phi, and z, but in the past time. So you could just be at rest at this point and go ahead and meet yourself here in the future. So this is a possibility in this space-time. So all the logical puzzles will occur. However, if you go back to this paper here, called Sauvé-Letellier, 1993, so we can they show that in this paper that you could generalize the space-time of a spinning cosmic string and also its location by using this metric here, which is also a locally flat solution of these equations. Okay, but what is behind that presentation is the following. He showed that in this paper that when S is more than kappa, the space-time is global hyperbolic. And in fact, you can show that the space-time with S is more than kappa is just the space-time of a cosmic dislocation. Okay, but otherwise, if you have S is larger than kappa, so it's a space that contains a CTC, and you can restate the space-time as the spinning cosmic string space-time, and that's all. Okay, so it's shown that they show that there. So the idea is now is the following. Well, okay, if S is more than kappa, so we have a global hyperbolic space-time. So quantum field theory works well. So I could do anything in this space-time which use all methods of quantization. So it's all okay. But if you arrive at this configuration here, we have problems. So we start working in this space-time. S is more than kappa. We look for solutions, and so you test what will occur if you take S and approach kappa algebraically. Okay, so okay, so I have time. So these are the Lorentz transformations that leads to the space-time with a cosmic dislocation only when you have S is more than kappa, and this here when you have a spinning cosmic string. So here you have problem. Here you don't have problem. So let's work in this space-time and quantize fields there. So I'll just summarize the results. I'm not going to detail about the calculations. These are in the papers. Okay, but the point here is the following. So I will assume S is more than kappa, and so I will do this. I will study the behavior of the solutions when S goes to kappa. So I will work in the flat coordinates like before, okay, as before, and so have the identifications of theta and psi like that. Kappa prime here is the square root of kappa squared minus S squared, and you remember that S is more than kappa in this situation. If I return here, you see that the Lorentz transformations that leads that general method to this one have a square root of 1 minus v squared, on where v is S over kappa. So when S is equal to kappa, we have a divergence here in this. But these are just coordinates, so it's not a problem in fact. So the same in the other side. So they are separated by this behavior. Okay, what the main result of that? So we calculate that, perform the calculations, use also the conformally coupled massless scalar field, derive the vacuum fluctuations, calculate the energy moment tensor, implement the back reaction. So, and just to show you an example, which is very similar with the method you use in Kerr space-time in order to define that region that people call as ergosphere in a Kerr solution. Remember that the place where you don't, it's not possible to have a reference frame at rest. So that a region. So here we have a very analogous situation, the S squared, which is invariant. So here we considered an observer initially at rest in this space-time, okay? And so the solution is this one here, okay? This part is appear only because of the defect associated with cosmic string, but this one is associated with the kappa and S in this case. But the space-time is space-time characterized by kappa prime, which is parameter now in this dislocation, this dislocated space-time. So the interesting thing here is the following. That's a manifestation of the the chronology protection conjecture effect in this solution. When S goes to kappa, so kappa prime will goes to 0, and this function here goes to infinity. So as you approach, when kappa prime is equal to 0 in this limit, we will be just in terms of having closed time-like curve in the space-time. Okay, so that's the entrance of a time machine in this case. But just before, before that occur, so we have a function here that comes from vacuum fluctuations that shows that it's just increasing, and so the fact that this guy here is a quantity that is always increasing will modify the background that you use to quantize the fields, and so it destroys the possibility of producing the solution. So it's a manifestation for the plus minus 2 is signature -2. So we need that is greater than 0, larger than 0 is Landau-Lisch signature. Yeah. Okay. So this is the main point. So if you take this guy here, which appear in the S squared, so you see that you have a region when this guy is more than 0, which will violate that condition that the S squared is always positive. The same you do in the Kerr space-time. So it defines a region. You can solve it for this coordinates here whole. Inside that, a cylindrical region, inside that, there is no possibility of having observed at rest. So as S goes to kappa, I'm just extrapolating because a back reaction, okay, procedure. If as S goes to kappa, this region widens the space and drags the observers in the Z direction. However, if you come back to the transformations, you'll see that as an observer moves in the Z direction, he sees this spinning quartz with fingers with a slower velocity. It's like, because I have a dislocation there, it's a more complicated thing. But in any case, it's a suggestion that quantum mechanics prevents the appearance of closed time-like curves. This is maximum we can do in terms of back reaction, as also Hawking discussed in this paper. Okay, that's the main points. I think I can stop here. And just summing up, but I'd like to remember that I have some collaborators here. Edson Moreira, my friends in Itajubá, Federal University, south of Minas Gerais, a beautiful place. And I have Edson Moreira, Leandro Gomes, and Renato Klippers that also took part of this collaboration. Thank you very much for it.
Questions?
When you have closed time-like curves, your space-time is no longer globally hyperbolic.
Sure.
So then you have a Cauchy horizon somewhere.
Yeah.
And they usually are unstable.
Unstable.
Do you think, usually, I mean, it's at least what happens in standard GR, they are unstable.
Okay.
Is it also the case in your model? Have you looked at the stability of the Cauchy horizon there?
Okay. If I understood your question, you mentioned about in the scenario that you worked. Okay, but you don't have that here because we are always in the global hyperbolic space-time. The only thing that you can conclude here is that when kappa when S goes to kappa, we approach that region in which we could find some problems with hyperbolic. So we were always there, always before this occurs. Yeah. Yeah, but what quantum mechanics shows is that there is a quantity that is taking large values, and so it will destroy the back reaction process behind that.
First of all, thanks for the lecture. My question is about the energy conditions. Did you see if they are satisfied by the scalar field that it generates, like
just
negative?
You have energy momentum tensor, and so you have the total energy momentum tensor must be a conserved quantity, even back reaction scheme. So you need just to avoid terms that like second order terms in H bar or things like that. But in the H bar order, so it's all consistent.
But
But
it's
the total energy tensor, I mean, it must be conserved.
it becomes negative at some point, or it
Okay.
always.
Your question is about negative quantities that appear there. Okay. Like here. In fact, I could be back to this. Yeah, here, for instance. Here, or also in the engagement tensor, because phi square is also appear there. So you see that you have negative solutions. So this is a negative solution of a squared quantity. It should be something puzzle, but it's not the case because you have renormalization. So in order to get physical solutions, so it's just subtract the vacuum, Minkowski vacuum contribution. And so you are comparing the result with a subtract, I would say, like that. So you can have positive or negative fluctuations. It's usual in this case. So you can have that. But you go back to the total energy moment tensor. Like here. In the order of the back reaction, this guy must be conserved, the total one. Because this guy is just divergenceless. Yeah. Okay,
Thanks.
thank you.
Any further questions? So I myself have a question. So can you go back to that page with the accelerations
last
with
one?
the, no, that page with the
Acceleration?
three components of the
Okay.
acceleration vector?
It is perhaps before,
No, it's after that, I guess.
after that, yeah.
Yes, that
Yeah,
one.
okay.
So you see in the first component, you have terms with different signs. So I wonder if that can be zero for some given initial condition
Okay.
or change signs if you just keep the evolution. Or if maybe it's always negative somehow.
It's a good question, Sergio. Let me just think a little bit. I think you have terms that I think this term here, if I need to confirm because it's a long time ago, but I think this term here is really dominant. This one here. So the
Which one? The first one?
What?
The first one, the one.
The first one, yeah,
Okay.
the A minus A. So the sign here would be negative in this component. And so
Yeah, of
you
course,
have-
because there's C
But if-
squared everywhere, but
Yeah, yeah. But if you have
but the corrections are always
very-
V over C squared. So
Yeah, I
those
thought-
could change sign, right?
yeah, let's suppose you have, for instance, theta and psi is equal to 0. So if you have velocities, very high velocity here, yeah, perhaps you could have
Maybe the contributions would
perhaps
change side, but the dominant term will always be negative,
Yeah,
right?
because dominant term is this one here. Okay, but in fact, beside that, if you have initial conditions, a very high velocity, you could just take it 0. It's very nice
Okay.
to see that.
Yes. So any further questions?
Good point.
No, so let's thank Vittorio again. So just before going away for lunch, you have the picture, the conference picture just outside next to the poster in the coffee break, right? So let's please go out there and then we'll be back at 2 p.m. sharp.
Vai ser sempre negativo.
Agora, para uma condição inicial em altíssima velocidade, pode ser que se anule.
Vão competir, né?
Isso.
Cara, não entendi um negócio. Assim, quando você pega aquele espaço-tempo de Mies, aquela conta de Konkovsky, primeira vez...
Hallowell Konkovsky?
Konkovsky, alguém outro...
Acho que é Hallowell.
Hallowell. Não, aí eles mostram que quando você tem CPC, o seu momento de energia renormalizado diverge no horizonte cronológico. Isso é a parada que todo mundo depois começou a repetir.
É patológico, né?
Então, se você tem a região acronal, quando você se aproxima do horizonte cronológico, o TMNI renormalizado, uma coisa split, diverge. E aí?
Mas no horizonte.
No horizonte.
Isso.
Mas isso é muito problemático, não?
Sem dúvida nenhuma. É por isso que você evita essa região. É por isso que você evita essa região.
Ah, você cobre.
É,
tá
não,
bom.
não tem, não,
Que você...
eu não tenho, eu não, não, também, aqui nem boundary condition porque você está num espaço-tempo que não tem.
Ah, eu
Entendeu?
tiro aquela região.
Você
da
teria
métrica.
quando o S vai para cá,
Tá bom.
entendeu? Então a métrica é completamente regular.
Vamos lá pro próximo.
Vamos. Sim. Deixa eu pegar a mochila ali. Vamos, o César também me chamou para almoçar? Vamos almoçar. Todos juntos. Nossa, quero saber das coisas particulares do nosso almoço aqui, né? Então, exatamente. Como é que desliga esse aqui?